Welcome back to section 2 of today's lecture on regression. In the previous video, I've discussed to you about the concepts and the techniques to do bivariate regression, which is relationship to look at the relationship between two variables. So in multiple regression, we wanted to know whether multiple independent variables can predict a dependent variable, or even more than one dependent variables. So we want to see what is the effect of each individual independent variable or predictor on the dependent variable. So we want to look at the intercept or the constant value, or the B0, and the slope, which is the beta coefficient, separately for each variable. And you should have learned by now that multiple regression is more powerful than a simple bivariate regression. Right? Because actually you throw in more independent variables to explain your dependent variable. For example, I ask you, how accurate can you explain your friend? If you explain that your friend, you've explained with one variable, let's say his age or her age, then it's not that revealing. You can only know, oh, because this person is about this age. But if you give me more information, that apart from age, this person likes a certain thing, this person dislikes certain things, this person lives in certain places, this person has this kind of skill. So I have more variables. So with more variables, it becomes more powerful to predict what I want to know about this particular person. So essentially, as you throw in more variables into the equation, your R-square will go up. Right? The ability of your independent variables to explain your dependent variable also goes up. So this is why the R-square is really much dependent on how many variables you throw in. Some people have this idea that you shouldn't do a laundry list of variables in doing your regression. That means that when you do regression, you have to have a theory. So if you don't have a theory, you just throw in a bunch of variables because it's likely to push up your R-square value. Then it's not really meaningful. Now, the regression that I've just shown you with the bivariate regression is, and what we'll do in the next slides, is what we call standard or simultaneous regression, in which all independent variables are evaluated all at once, all together, right? Because we want to test all of them. So we don't have any particular structure or speculation or hunches which ones are more important than other, or which one that we want to test in certain blocks, if you like. So if you want to test it in a certain blocks because you have a certain theory, you use hierarchical regression. So the hierarchical regression is typically used to evaluate independent variables that is determined by theory, right? So you are actually comparing a null model or model 0, basic, with model 1, model 2, model 3, model 5, model 7, depending on how many that you have, right? Because you have a research model or hypothesis to test specifically, then you can use this hierarchical regression. And we also have others called stepwise regression, the forward one and the backward one. So we're going to look at this in a moment. So just a quick one. The forward one is the independent variables that you enter in the system is evaluated one at a time by the algorithms, right? So you will add one more and one more and one more until a certain critical value is met or not. Then you will have a model, the final model. But in a backward approach, all the independent variables are evaluated all at once, and some will be removed step by step if they didn't perform well, and you have actually the final model. So let's have a look. So in multiple regression, you're interested to examine the separate effects of multiple independent variables and also control for some correlation of your independent variables. Remember we talked about the assumption testing on multicollinearity in the previous video? So when you have a very high correlation among your independent variable, this is called multicollinearity, and you don't want this. So actually, when you have multiple variables or multiple independent variables that you enter into your regression, you are kind of controlling each other, controlling let's say you have 4 independent variables that you regress on your dependent variable. So by entering 4 independent variables, you are controlling them with each other. to see if they are too high related with one another or not, right? So if just to refresh your mind, in the simple correlation, right, you have one dependent variable, the y, and one independent variable, the x1. So the x1 has nothing to control for, right? But in a multiple linear regression, you have the y, the dependent variable, right? And you also have multiple independent variables. You have x1, you have x2, you have x3, x4, xn. How many x is called xn, right? So for every x, you have a beta, the slope. So x1 has its own slope called b1. x2, let's say this variable is called gender. Gender has another slope called b2. So this is just a symbolic representation of this equation. Now, in multiple regression, you're going to get this type of model summary and coefficients. So you can see, for example, look at the predictors down at the bottom of the first table. You have sex, you have education level, two variables to predict the beginning salary, right? To predict the beginning salary. So the R square is 0.462. So that means 46.2% of the variation of the beginning salary can be explained by sex of the employee and the education level. But the question is, how much is the additional change created by adding another independent variable? So you could do this by having just a sex employee and look at its effect on the relationship with the beginning salary, and you add another one called education level and look at how is this. But this is called the hierarchical. But if you just look at these two together as a simultaneous, you have the sex and education in predicting the beginning salary, and the R square is 0.462. And what you're more interested in is actually the coefficients. Right? The coefficient. Look at the standardized and unstandardized. You can use whichever you like, but it seems that when you're comparing across variable, it's nice to use the standardized coefficients. Look at that. Education have 0.539 and is significant at 0.000, and the sex of an employee is minus 0.265 for standardized and it's not significant. But if you want to look at unstandardized, like how much is the impact of education level in terms of dollar, is $588 positive influence on the beginning salary, while for gender is minus. I think this means that female will have some penalty in terms of their salary. So the closest someone to female, being female, they're going to have a negative salary. So this one, negative 1672. So we can report this as the intercept, and look at the constant. It's minus 366, and it's not significant, 0.533. So it's not significant, right? So you can make a conclusion. The intercept or the constant was not significant. Regression terms for the sex was minus 1672.307, and for the education level is 588.128, and both were significant at 0.001 level. And the beta values show that the educational level was a stronger predictor. Look at education is 0.539 and the sex is minus 0.2. So just look at the actual value. So one has a higher value than the others. So it has so the education has a stronger predictor than strong predictor for beginning salary than gender. Actually, gender has a negative influence. So between education and sex, you can say that, well, education has more influence than the sex. So this is how you represent your regression, multiple regression equation. So you write that current salary 366.27 is the constant or the intercept. So current salary equals to minus 366.27 plus 588.12 multiplied by education level minus 1672 multiplied by sex. So the conclusion is the same as the previous slide. So this is just how you write it up. Let's say there's another example from another study here from a data that you can click from that web link called from a SPSS tutorial somewhere that have been posted from the internet. So a researcher is trying to understand if and whether healthcare costs that people are paying can be predicted by their characteristic as a patient. So you're looking at sex, you're looking at the age, how much they consume alcohol, how much they consume cigarettes, and the hours of exercise per week. So you're going to use this 1, 2, 3, 4, 5 independent variables to predict the total healthcare cost as a dependent variable, right? And you have this result of the model summary, in which the one at the bottom, the model summary, it says that all of these independent variable have an R-square of 0.395, which means that 39.5% of the variation of the total healthcare costs can be explained by all of these 5 variables, right? Sex, blah, 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 hours of exercise. And then important part is you want to write a regression equation. So you can write the dependent variable or healthcare costs equals to the intercept, or the constant is minus 3263, which is minus 3263, plus 509.27 multiplied by sex, right? And then 114.6, 1.4.7 multiplied by age, right? And then 50.4 multiplied by alcohol consumption, and plus 139.4 multiplied by cigarette consumption, and minus 271.27 exercise. So look at this one. Along this regression equation, most of this variable will increase the healthcare costs, right? So the age, as you grow older, the healthcare cost is going to go higher. The more someone consume alcohol, the higher the healthcare costs. Look at the cigarettes, it's also positive. The more people smoke cigarette, the higher the health cost. But look at exercise, it's negative. So which means that the more someone do exercise, the healthier they are, which means that it will push down the healthcare costs. So healthcare has a negative relationship with healthcare costs. So you can interpret this also. A 1-year increase in age results in 114.7 increase in the healthcare costs, or a 1-hour increase in exercise per week is associated with minus $271.3 increase, or you can also say it decreases to 71.3 for the healthcare cost. So this is how you write it up. So importantly, there is some convention in how you write the results, right? So you have like the top table is just the descriptive statistics table with some correlation, the mean, the standard deviation, the correlation among these 5 independent variables, right? And then you have the main coefficient, regression coefficient, the second table down there. You have the beta value, confidence interval, and standard and non-standardized, and then they have a t and a p value. So you can write up like the hypothesis was tested using a random sample of 525 subjects. Model R-square is 0.395. Look at the previous table, and which is significant at 0.0, which where do you get 0.395? Yeah, the model summary. Look at the number 2, 0.395. So that's how you get it. So model R-square is 0.395, which is significant at 0.001, and F at the degrees of freedom 5 and 5.19. Yeah, degrees of freedom 5 and 5.19. Look at the regression and residual under the DF column, 5 and 5.19. So F 5.519 is the F value is 67.89 and it's significant. So you can say that the intercept term was significant, right? And the beta values indicated that sex, age, alcohol, cigarette consumption, and exercise was significant predictors of health costs. And thus the regression results support the hypothesis that you are proposing. In the second part, so that is the result for multiple regression, right? So I can continue this with the hierarchical. So when you have a theory that you want to test, right, and you are using multiple regression, you have multiple independent variables, you can use a very specific technique. For example, according to the literature, you have a theory that healthcare cost is typically or mostly driven by the lack of exercise for people. So your main interest is to test that physical exercise, whether people have exercise or not. That is actually the main one. But you also know there are other correlates or other variables that also predict the the total healthcare cost, and you know that, oh, smoking and alcohol consumption are also important, but you don't know how important they are, right? So in essence, you want to control for the effect of smoking and alcohol consumption when you test this variable on exercise, how much people do physical exercise. So when you do the regression, hierarchical regression, right, you can first enter these variables that you want to control for, such as the alcoholic consumption and the cigarettes. And this is called the block one. So you enter your dependent variable, enter your independent variable in SPSS. That's called the block one. And you click next, and you enter the next one called the physical, the hours, average hours of exercise. So that's the block two. And you choose the statistics and choose the estimates. And important part is the R-squared change. And for the options button, you want to use the probability of F. And your entry is 0.05, and you remove when they are bigger than 0.1. Right, so that's how you instruct the algorithm. So, and it will speed out the results. So this is an example of that from that data set. So it shows you which variables were entered. So look at that. Model one. Look at what is your dependent variable. Dependent variable is total healthcare cost. Look at model one. You include consumption of cigarettes, consumption of alcohol, right? And then that's a step one, right? Or model one. And a step two, model two, you include the exercise per week. And you can look at the model summary. When you only include two variables, which is the cigarette and alcohol consumption, your R-square is 0.228. And the F is 76.9 and significant, right? So the model one is significant and can explain the two variables called cigarette and alcohol consumption can explain 22.8% or 0.228 of the total healthcare cost, right? And then when you add another variable called exercise per week, which is model two, look at the B1 under the model summary, the B1 at the bottom, predictors. Now your predictors or your IV, you have consumption of cigarettes per day, consumption of alcohol, and average of exercise per week. So now you have 3 instead of 2. So in model 2, you have 3 independent variables there. And look at the change in R-square. Look at R-square. In total, compared to model 1, in which your model 1, you only have cigarette and beverage consumption, the R-square is only 0.228. When you have 3 variables by adding the hours of exercise per week, the R-square becomes 0.289. Right? But how big is this change? Then you look at the R-square change. So R-square change is 0.061. Tiny, but is this tiny significant? Look at the F is 44, it's big, much bigger than 1 is quite big, and then significant at less than 0.001. So you can say that by controlling for this first 2 variable and adding the main variable, which is your exercise per week, the model is significant. So you look at the ANOVA. So look at model 1 when you have only 2 variables, cigarette and alcohol, is 76.9 is significant, and when you add the third one, F is also significant. And the key part is actually this, the coefficients, right? So you can see, for example, here, when you have only 2 variables in your model 1, look at the coefficient table, right? When you only have alcoholic consumption, it's 60.28 there, right? And the standardized is 0.23, right? And compare that with your model 2, in which you have 3 variables. So you have alcohol consumption and cigarette consumption plus exercise. Look at the value of the alcoholic consumption. It drops from 60.288 to 40.903 for the unstandardized. And you can also look at in the standardized column from 0.23, it drops to 0.156 and still significant, right? That will make you think why. But before I tell you the full story, look at the second one, the consumption of cigarettes. When you have only 2 variables in model 1, the consumption of cigarettes is 148.55. Now, when you add exercise per week in model 2, that unstandardized B coefficient for consumption of cigarette drops from 148451 becomes, it dropped to become 121.69. And the same for the standardized one, from 0.332, it dropped to 0.271, and also significant. And why is it dropping? Because you have another variable that you entered in the system, in the regression. And that variable is called exercise per week, and it has -263, and it has -0.272, also significant. So in essence, you're controlling the effect of alcohol and cigarette consumption in order to know how important is exercise per week, right? Sometimes, so this happens that even you control for the first two variable, and you enter your main variable, which is exercise per week, you get all of these variables significant. But in some regression, or in many analysis even, when you enter a certain variable, the previous variable becomes insignificant. So for example, you add the first two variable and they're significant, and you add the third variable in the second model, it could make one or both of the previous variable not significant. It's possible. So this is why this hierarchical regression is quite interesting. So when you do this hierarchical multiple regression, you will have this VIF value, variance inflation factor, and variance inflation factor tells you about collinearity. So the rule of thumb is look at the value of VIF. So when it's greater than 5, is considered potentially severe collinearity, multicollinearity. So it's dangerous. It means that, you know, the beta coefficient may not be reliable. The p-value may not be reliable, but it's when it has around 1, between 1 and 5, that is moderate, but it has perfectly a value of 1. It means there's no correlation between the IV and other IVs. So actually, between 1 to 1 to 5 or 1 to 3 should be okay. So the result here, look at the main model. Model 2 is the one that we rely on because it's most complete, and it's the more complete model. We have all the variables entered, and look at the VIF, they're all 1 point something. So we can say that there's no collinearity problem among the 3 independent variables in the model. So this is fine. Outlier is another issue. So when you do outlier, you can actually, when you do the regression in the plots, so there's one button for plots, you can enter the Z-score of the predictors and the residuals. So for example here, the Z-score for the predictor, enter as X. X is always a predictor, and Z-score for the residual. Residual is the outcome that you want to know. So X on Y, and you tick for normal probability plot, check it, and it will give you the graph in the middle. So you can see that your data is actually the thick line there. It's actually, they are circles, but they're too close to each other, so they become like a very thick line. And the regression line is the diagonal one, right? So you can see your residual, right? So just look at the observed and the expected, right? The observed is expected. When it's perfect, it has this perfect diagonal line. But the one that we have there, the standardized plots, is quite close to the diagonal line. You know, the thick curvy line is quite close to the very straight diagonal line. So you can see that the residual is quite close. So that means that it's still relatively normally distributed. And look at that, a plot between the standardized predicted value on the X and the regression of the standardized residual. It has no pattern. And this is good. This is good because remember when you go to the formula on how you calculate the residual is the distance from each observation from that main regression line, and the further that observation is from the regression line, the bigger is the error. So you don't want to have your predicted value and your error to be so closely related, right? So when you have these things very much scattered everywhere, it shows that your data is pretty much fine. There's no serious outlier problem. So what is outlier? Outlier is when your data is so much far away from the norm, from where every other data points are, right? And the residuals is looking at the actual value and the predicted value. Predicted value is that line that you're predicting using the regression equation. And there's this distance, and that's called the residual. So it's the actual minus predicted, right? So when your predicted values and your actual values and predicted values are very close to each other, then they look fine, like the one in the middle. But look at the one on the most right, my right, when you plot the predicted values and the standardized, when they have no relationship, then that's good. That means there's no problem. There's also some Mahalanobis distance. We're not going to look at it, but when you do your regression, it will produce Mahalanobis distance. Looking at the table there that I highlighted in a circle in red, and looking at the chi-square distribution table, which you can download anywhere, type chi-square distribution. So we are using a p-value of significant value of 0.05, and you have 3 variables here. Remember the consumption of alcohol and cigarette consumption and exercise. So you have 3, and then DF of 3, and you go there, it meets at 7.81. So actually our Mahalanobis distance is 24.5, which is much bigger than the chi-square critical value of 7.81. So that means there's something serious that we need to fix it. So when you have this outlier problem, then you have to re-examine your data, correct your errors. Maybe you remove some observations that have errors from your data in Excel, or you do a mean replacement, or you may need to transform your dependent variables using some log transformation, etc. And you can rerun again. Or if your extreme value outlier is too serious, too extreme, you really need to remove them. And this is how you write your hierarchical regression sort of conclusion. In the same way as you write any type of regression, you have model R square, and you show that your first model and your second model and how they changes. So this is very important. And this is another study from a paper that I found is quite interesting. So they have quite a complicated model to test. Remember, use hierarchical regression because you have a theory. So they want to test this. So look at that table 5 down there. So the first control for 3 variable, enterprise age, scale, and nature. So that is the key that they want to control. And the part that they're interested in is the proactive market orientation model for model 1.1 and the proactive reactive market orientation for model 1.2. So these are the 2 they're very interested in. So they enter them in regression, in hierarchical, step by step. And the key part that they want to test is that interaction between the proactive and reactive. And they found all of these things are significant. And the R square are there, and the F test is all significant. And that is how they test the relation between market orientation and digital innovation. But there's another table, the table 6, that shows you how they test that the green one. Remember the green one that I show you there? So they want to look at the relationship between the proactive and reactive market orientation on social capital, how they interact to affect the digital innovation. Digital innovation is the DV. So you can they do it in a block by block. Like first step, model 2.0. That's the first model, and model 2.1. Right, they enter the proactive market orientation and the social capital, and then the interaction. And the next model is the reactive and social capital and the interaction between reactive and social capital. So in the same way, you can generate that, and they report the results like this. So we use hierarchical regression. We have model 1 that shows that it is, and this was supported, and model 2 like this also supported another hypothesis, and model 1 to 3 have this interaction analysis and is confirmed the hypothesis. And that's for table 5. For table 6, you also say you have done the hierarchical regression. Model 2.0 is the basic model. Model 2.1 shows this interaction between the proactive market orientation and social capital is significant, and it shows the hypothesis 3A is verified. And model 2.2 looking at the interaction between reactive market orientation and social capital, and again, the beta value is 0.2, and it's not significant. It's more than 0.05. So you can say there's no relationship between reactive market orientation and social capital, things like that. So that's how You can also do a stepwise regression in a forward and backward approach. So in a stepwise regression in a forward approach, you enter your model all at once, but you tell SPSS to do the evaluation step by in a forward approach. So it's a kind of hierarchical, but you ask. So in hierarchical regression, you enter that purposefully because you have a theory, right? So in stepwise regression, it's more like exploratory. You are doing exploration, and you let SPSS to add variables gradually. So for example, the same, I'm interested in the total healthcare as a dependent variable, and I enter these 3 variables: alcohol, cigarette, and exercise. And I use forward, and then it will speed up this result, right? Model 1, model 2, model 3. So it considers each variable one by one. The key part is looking at the model. Look at the model summary, right? So for the A, you have only cigarettes, right? And the R square is 0.184, right? And it's significant. The F is significant. And then for the B, look at the small b down there. You have the cigarettes plus exercise per week, right? And R square is 0.27. But how much is the change of the R square by adding exercise? Exercise is the second one, right? By adding the exercise, it becomes 0.086. So it's much smaller than the previous 0.814. And it's also significant. And for the C, the one at the bottom, you have what? You have cigarettes, you have the exercise, and you have consumption of alcoholic together. All 3, right? And then the R square is 0.289, so it keeps increasing. So you add more independent variables, the R square keeps increasing. But look at the R square change. It's changing, but it's getting smaller. The change is getting smaller, but it's significant. And you look at the ANOVA table, all F are pretty big, much larger than 1, and all significant. So you can say all of these models are significant. But when you look at this coefficient value, you can also look at the first one, model 1, model 2, model 3. I like model 3. You can look at model 3 because I think perhaps it's the most complete one. Actually, when you compare this result with the hierarchical regression, the result is pretty much similar. So it's nothing different. No, another one is called stepwise but backward approach. So again, you use stepwise regression because you want to explore the data. Let's say you have multiple independent variables that you want to explore, but you let SPSS to do the estimation by gradually remove. So it put all variables at the same time, and it slowly removed some parts until the best one was found. So again, with the same approach, you have a dependent variable that you enter and 3 independent variables that you enter, and you go for backward, right? And it shows you this approach. Your dependent variable is total healthcare and variables that you enter all at once. And the model summary, it gives you just one because it finds that only one model can best explain the results. Actually, these results is very similar with the previous forward approach. Have a look. Very similar because I use exactly the same variable. But you could have a lot of independent variables, and you are exploring them using stepwise forward or stepwise backward, and you can which one works better, right? So yeah, so that is gradually. So you can also have a stepwise approach. In SPSS, they have forward, backward, and stepwise. Stepwise is actually adding and removing. So it's stepwise regression. The stepwise approach is actually a combination of forward and backward. So they're combining together. And they will produce results. And again, you look at the last model, model 3, look at the coefficient, look at the model 3, that is kind of like the most complete one that you want to see. And you want to see the changes in R square and the changes in the coefficient, unstandardized and standardized coefficient. Look at how they change. So I ended there for the multiple regression using the simultaneous, hierarchical, and stepwise regression. So this is just to give you like the different techniques. So normally you need to have a very strong reason why you want to use hierarchical, why you want to use stepwise. But in common sense, in a common approach, people use simultaneous regression, which is a regression where you enter everything all together at the same time without worrying too much about which variables goes first in the model testing. Thank you.